Right, back with the examples for the derivative of exponential functions. I knew you couldn't wait. So let's have a look at these different examples of asking you to differentiate here. Just give a bit of space, but more space between each of these. And right, so we're going to use this rule that we got up at the top over here, and we're going to apply that to each of these examples. So in the first case, if y is equal to e to the power of 1 minus x, dy dx is going to be the derivative of d of 1 minus x, don't cover the knot, 1 minus x all over dx times by e to the 1 minus x. And the derivative of 1 minus x is simply going to be minus 1. So it's going to be minus 1 times by e to the 1 minus x. That's what my derivative is going to be. The second example, well, this is not just an exponential problem, it's also a product problem. So we need to think about this as having two parts. There is u and there is v. So du dx, derivative of x, that's simply going to be 1. dv dx, well, that's going to be e to the x minus 2. Well, that's simply going to be 1 times e to the x minus 2. The derivative of x minus 2 is just 1. So if I want to work out what my derivative is here, it's derivative of a product. So we're going to start out and say it's going to be u, which is x, times by the derivative of v. So that's going to be e to the x minus 2 plus e, which is e to the x minus 2, times by the derivative of u, which is simply going to be 1. And you'll notice now that I have a common factor over here of e to the x minus 2, and I'm going to be left inside the bracket with x plus 1. There is my derivative of that product involving an e function. The next example, the example that's going to use the quotient rule. So what have I got? Here is my value of u. Here is my value of v. So I can work out du dx. Quite simply, that's going to be 3x squared. dv dx, that's going to be derivative of 2x, which is going to be 2, times by e to the 2x. Now we've got to make sure that we get this in the right order. If we look at the formula sheet for a quotient, it is going to be v times du dx minus u times dv dx all over v squared. So we now need to apply what we've got here. V is e to the 2x. du dx, well, that's going to be 3x squared, minus u, which is x cubed, times by dv dx, that is 2e to the 2x. And all of that is going to be put over v squared, which is e to the 2x. And I'm going to square that. Now I need to tidy this up because I've got common factors present all the way through. I've got an x squared that's present in both terms in the top line, and I've got an e to the 2x. So I'm going to take out x squared and e to the 2x. And what am I left with? I'm going to be left with 3. That's all I've got from that part. Minus, that's going to go, and I'm going to be left with 2x cubed. And all of that's going to be over e to the 4x. There is the derivative of that quotient. And then they could ask you something nasty like this. The derivative of a square root. Well, we don't need to be too concerned about that because we can always write this as e to the 3x minus 2 raised to the power of a half. In other words, I simply multiply the powers now. I'm going to get e to the 3x over 2 minus 1. So if y is equal to e to the 3x over 2 minus 1, then dy dx is simply going to be the derivative of 3x over 2 minus 1. That's simply going to be 3 over 2, multiplied by e to the 3x over 2 minus 1. So it looks a lot worse than it is. Now, obviously, with these problems with differentiation, they can go and pull in questions that ask you to find stationary points or normals to curves. And that's what we've got here in this part. Right, we're going to look at this equation, this problem now. We want to find two stationary points for a function that involves e. If we're going to find stationary points, we need to find turning points. If we need to find turning points, we need to find the points where the gradient is equal to 0. So, first thing we're going to have to do is to derive this function. So, dy dx. Now, we should notice here that we've got a product. So, you've got your u, you've got your v. So, it's a simple product that we need to figure out. So, we're going to say it's going to be v, so in other words, e to the minus x times by the derivative of u, so that's going to be by 2x. And then to it, we're going to have u, which is x squared, multiplied by the derivative of v. Derivative of e to the minus x is going to be minus e to the minus x. And so when I tidy all of that up, I'm going to have something like this, e to the minus x, 2x times e to the minus x plus x squared, e to the, it's not plus, is it? It's going to be minus, minus x squared e to the minus x. And of course I can factorize that by taking out 2x, no, I can't take out 2x, I'm going to take out 1x, x times e to the minus x, and then I'm going to be left with 2 minus x. And we want to know where dy dx is equal to 0. So in other words, we want to know where this thing, x e to the minus x times 2 minus x equals 0. And so either x e to the minus x equals 0 or 2 minus x equals 0. In which case here x is going to equal 2. In this case, e can never equal 0. So the only way that this thing is going to equal to 0 is if x is equal to 0. So there we have the 2 points where the graph has stationary points, or the curve has stationary points. All we need to do now is to figure out what the corresponding y values are with these. In this case over here, if I go and put 0 in there, I'm going to get 0 times something, so y is going to be 0. If I go and put y is equal to 2 into the other expression, I'm going to get 4 e to the minus 2. And in fact, I'm not going to bother taking that out any further. I can leave it like that. So there are my 2 points, x 0 and 0, or 2 and 4 e to the minus 2. And hopefully we can see that this one over here is going to be our maximum, and this one over here is going to be our minimum. And in fact, the curve, when you draw it, looks something that looks like that. And it crosses over here at the origin. So there we've got our two stationary points. Finally, we need to look at this problem here. Give the equation the normal to the curve. Again, I've got a product at the point 0, 1. So again, I need to stipulate my u and my v values over here. And straight away I can launch in and say, right, dy dx is going to give me v, which is e to the x over 2, times by the derivative of u, which is simply going to be 1, plus u, which is x plus 1, times by the derivative of e to the x over 2, and that's simply going to be a half e to the x over 2. And if I tidy that up, I'm going to get e to the x over 2 plus x times by a half e to the x over 2, and then I'm also going to have another half e to the x over 2. So in other words, I'm going to have 3 over 2 e to the x over 2 plus a half x e to the x over 2. If I go and factorize that, I can take out a half e to the x over 2, and I'm going to be left with 3 plus x equals my derivative. Now in this example, I don't want to find a turning point or a stationary point. I want to find the normal to the curve at this point over here. So I need to see what is the gradient at x is equal to 0. At x is equal to 0, what am I going to have? I'm going to have a half e to the 0 times 3 plus 0. In other words, e to the 0 is just 1. So in other words, I've got 3 over 2. So that's the gradient of the tangent. So in other words, the gradient of the normal is going to be the negative reciprocal of that, which is going to be minus 2/3. And so my equation, when I come to work it out, is going to be y minus 1 is going to be minus 2/3 x minus 0. In other words, y is going to be minus 2/3 x plus 1. That is the equation of the normal at the point when x is equal to 1. Hope that helps. Now you need to go and practice these. Good luck. Goodbye.